We're going to kick off with Eric Murphy from National Radio Astronomy Observatory, and he is going to speak about the next generation very large array.
Thank you very much for inviting me to talk about the next generation VLA. I think, honestly, the last time I took a trip to a conference before the pandemic, it was in South Africa, in Durban. I wish I was there now in person instead of here, but hopefully soon in the future. Like Oleg said, I'm going to talk about a next generation VLA, which is what NRAO's probably largest initiative right now. It's a new radio telescope, which will be a transformative new facility that will be replacing both the Very Large Array and the VLBA simultaneously. And the new scientific frontier it's aimed to tackle is thermal imaging on milli-arc-second scales, which for those of you who are radio astronomers knows it takes a lot of steel on the ground. The thermal sources are faint, and to detect them at high angular resolution really takes a lot of collecting area, which means a lot of telescopes and a lot of data collection. The ngVLA aims to be, or is designed to be 10 times more sensitive than the VLA and ALMA, where the bands overlap with ALMA at lower frequencies. It will achieve 10 times higher or even more, actually, angular resolution than the VLA and ALMA. The frequency range expands what the VLA can do right now in its typical configuration. So instead of just going up to 50 gigahertz, the next generation VLA will cover 1.2 all the way to 116 gigahertz. So that is accessing atomic hydrogen, the 21 centimeter line, at 1.4 gigahertz, and going all the way up to CO, the lowest fundamental transition of CO, at 115 gigahertz. So being able to both measure atomic gas and molecular gas in nearby sources. The array consists of 244 18-meter offset Gregorian antennas, which is complemented by 19 6-meter antennas to fill in, sort of do the short spacing array to fill in the holes left by the 18-meter antennas, as well as some of the 18 meters used in total power mode to fill in that for zero spacing. So basically, it follows the kind of how what ALMA does to detect emission at all angular scales. It'll be located centered at the current VLA site, and most of the antennas are in the existing VLA footprint, at least out the A configuration, but spread over the U.S. Southwest, or concentrated over the U.S. Southwest, and really spread across the entire North American continent. Antennas will be fixed, not reconfigurable like the current VLA, so similar to the SK and ALMA. So what the ngVLA does is really links both the SK and ALMA scientifically. So on the left, you can see what is plotted is basically sensitivity as a function of frequency. And it doesn't go all the way down to, where the SK will be at the lowest frequency end, or where ALMA will be at the highest frequency end. But the ngVLA really sits right in between these two premier facilities, and it's really like sort of a final showcase or a showpiece to this next generation of suite of radio interferometers. So where the ngVLA is optimized for at 1 centimeter, it's really superb for where the ngVLA key science goals you'll see is for terrestrial planet formation, looking at the dense gas history of the universe, and baryon cycling in nearby galaxies. On the right, you'll see angular resolution plotted as a function of frequency, and this really, nails down what the instrument is meant to do. So that maroon line here indicates the angular resolution necessary to achieve 1 AU resolution. So that's the distance between the Earth and the Sun at a distance of 140 parsecs. So that's the distance of the nearest major star forming region, where there are hundreds of protoplanetary systems. And so, as you can see with this line, the ngVLA is able to detect forming planets, Earth-like planets on AU scales, on Earth-Sun distance scales. And you can see over here on the right, the ground-based large optical telescopes, the ELTs, TMT, GMT, they're trying to do the exact same thing, achieve that angular resolution, but instead of being able to detect the planets as they are forming, they're going to be detecting the planets that have already formed. So it's a very nice complement to what the OIR community is trying to do with their next generation facilities. The ngVLA project has an org chart. just showing this to make you all understand it's pretty official. We have a project director, which is Tony Beasley, who's also the NRAO director right now. Two project managers, Jill Myers and Willem Esterhaus. Willem Esterhaus used to be in South Africa. I am the project scientist. Rob Selina is the project engineer. Our system engineer also comes from South Africa, Thomas Kuzel. And we have a cost analyst, Alexia Nelvik. We have 10 integrated project teams. And the way our project is set up is to be is for seamless entry into the National Science Foundation major research engineering facility construction project definition. So that's where big facilities in the U.S. Are funded to be built, and we're looking to get into to become a candidate at that very soon. And we have very active community participation through science and technical advisory councils. They've really been critical in steering the design. I think if you spoke to any of them, they would agree that they've had, they've been, key members of the entire process, which I think is important. And what has made us, whatever success we've had is because of that. So the telescope is designed to really carry out a broad range of studies. Here I list them, the 5 key science goals that were derived based on a use case capture from the community. Over 180 of individual observations were captured by community members. We gave them basic instructions. What would you do with a facility that had 10 times the sensitivity of the VLA and maybe, had frequency coverage up to 116 gigahertz? And we got a broad range of responses, which really shows that the community, at least the US community at large, really wants a telescope that they can dictate what the project is. Not a survey style telescope like LSST, but something where they can carry out their own investigation. So the 5 key science goals go from unveiling the formation of solar system analogs and terrestrial scales, something I already mentioned, probing the initial conditions for planetary systems and life with astrochemistry, something that's also uniquely done at sort of centimeter and below frequencies, charting the assembly, structure, and evolution of galaxies over cosmic time, using pulsars in the Galactic Center as fundamental tests of gravity, and understanding the formation and evolution of stellar and supermassive black holes in the era of multi-messenger astronomy. So yes, very broad, a disparate set of science goals, and the design of the telescope has been set to achieve each of these science goals. So the first one is unveiling the formation of solar system analogs. So on the left here, you can see the pretty famous image of HL Tau, showing rings around a protoplanetary disk. Below, you'll see a zoom in. It's a simulation of a solar system-like, sort of a Saturn, Uranus, Jupiter, and Neptune mass planets forming around a solar-like planet. This was done by Luca Ricci to show you what the ngVLA will be able to see. And given the number of systems that will be available to the ngVLA, there'll be somewhat of hundreds that have orbital periods of less than 10 years. So this image this animation to the right shows that not only will we be able to study these protoplanetaries statically when just making images, but we'll be able to revisit them over time and watch the planets form in situ, in real time, which I think will be an absolute game changer in the studies of planet formation. And the image in the middle just shows what's achievable in the numbers given the number of known planetary systems that could be detected and resolved by the ngVLA compared to what ALMA can do and the future ELTs and what is currently done now with existing telescopes. Another key science goal, I'm not going to go over all of them, but another one is charting the assembly and structure and evolution of galaxies from the first billion years to the present. So the ngVLA frequency coverage and sensitivity allows us to measure low J transitions of CO over at all redshifts. And why this is important is because by accessing the low JCO, you trace the bulk molecular gas of galaxies, which is a qualitatively different picture of what you get with existing element observatories when you measure the higher J transitions. So the higher J transitions really trace the warmer, dense gas, while the low J transitions trace the bulk colder gas. And this is shown in the simulation up here. So on the left, you see a simulated image of ALMA. The CO, the transition is J equals 4 to 3, which is really showing you just the center of the gas, where all the action's happening, the warm gas that's actively participating in star formation. In the middle panel, you see what the ngVLA could do with by accessing the J equals 2 to 1 line. So you see more diffuse or cold molecular gas surrounding the central star forming region, but for the most part, it's pretty centrally concentrated. In the right, you see what ngVLA will pick up by going and detecting CO equals 1 to 0, which again is a qualitatively different picture of what you get with ALMA. So if you wanted to know what the bulk, how much molecular gas are in these galaxies at high redshift available for star formation, without having access to this low J line, it's almost impossible to figure out. And then the last one, key science goal I'll go over is that of understanding the formation and evolution of black holes in this new era of multi-messenger astronomy. So the ngVLA will be sensitive to black holes of all masses. We can have searches in the galaxy, largely followed up by some other sort of observational tag, and go in to see if we can detect any accreting black holes, again, of all masses. But the really cool thing, I think, is that with the long baseline, the very long baselines of the ngVLA, cross-continental baselines, we'll be able to, unaffected by dust, have the sensitivity and the resolution to resolve dual AGN and black hole binaries. And with the sensitivity available, measure proper motions over 5-year periods of expanding jets from these potential gravitational wave sources. And this is shown in the plot on the right, the projected nuclear separation of the sources as a function of redshift. And this orange area shows you exactly where the ngVLA will be able to have the sensitivity and the resolution to look at these expanding kilonova events from gravitational wave sources. So I think that's super cool. To date, we've had strong community participation, both in the US and abroad. This is a smorgasbord of logos. You'll see in the left, mainly US institutions. We have interacted with the private sector, industry, and then a number of international partners who all participate either on our advisory councils, through our community studies program, as well as our technical advisory councils. To date, I think we've been pretty successful at community engagement. Of course, that looks a lot different now than it did a couple years ago when we were having more in-person meetings. Hopefully, we're starting up on those in much more full force soon. But even through COVID, we've been pretty successful at hosting Zoom short talk series over the past couple of years. We've run our community studies program, which has been extremely successful, where we go out to the community, both international and in the US, and ask for people to look into different areas that either we don't have in-house expertise or don't have the person power to conduct such studies. I mean, one example is RFI studies. In South Africa, EMSS has been helping us with our receiver feed studies and our optical design efforts. We've also hosted a number of ngVLA town halls, and I think we're doing the best we can with what we got, and I think because of that, we get pictures like this, which contain many people who I don't usually see. I mean, a lot of times when I was going to radio conferences, it was all the same people, but I think we're very similar to the SK, able to generate. We're getting a younger, new. Early career group of people excited about the telescope. International engagement has been ongoing since the beginning. The members we have a group of international members that participate in our science and technical advisory councils. This includes Canada, Mexico, Japan, Germany, Netherlands, and Taiwan. Right before COVID, just before this, the meeting, I was in South Africa. I was in Japan for our first international science meeting. In Mitaka, hosted by NAOJ. And the Japanese right now, actually just a couple of weeks ago, just released their own ngVLA science book, which is completely in Japanese. They have their own website, and they are being considered as the ngVLA is being considered as part of the Japanese master plan in 2023, which is similar to this US decadal process, where a bunch of, presumably very smart people set the priorities on where government should fund money for science. And also for the Canadians, they just went through their decadal sort of process, the long range plan. And the Canadian, the recommendation there was to be a 6% partner in ngVLA, which is exactly the same percentage I think that they are for SKA. So what does the instrument look like? The technical baseline is here. Frequency coverage, like I said, 1.2 to 116 gigahertz. We have a main array of 214 antennas, which are spread across the US Southwest. About 75% of them are within the existing A configuration of the VLA, and the rest of those then are sort of spread out to 1,000-kilometer baselines into neighboring states in Mexico. The short baseline array that I already mentioned, and then we have a long baseline array of 30 18-meter antennas, which fill up the existing VLBA sites and plus another few. There are 3 antennas at each location, so giving us the full VLBA cross-continental baselines of up to 9,000 kilometers. Here's some images on the distribution of the antennas. You can see to the left here, the US Southwest. Then we have this 5-arm spiral here with a central 4-kilometer core. This then expands into 5 other arms, which go into the neighboring states. And then up here in the right, you'll see these purple sites. These are all the long baseline sites. They're sort of paired for phase calibration purposes. We tried to keep them within sort of 1,000-ish kilometers of one another. So that's the reason for that. The antenna concept here is the current design by MTEX, who we've contracted out now to build a prototype. It's a feed load design like the SK for maintenance requirements. We have a mount concept and well, I guess we lean towards still pedestal. We're going with the pedestal concept. Direct drive motors and traditional panels with steel and bus and composite reflectors. Right here, you'll see key specifications of the antenna: 18-meter aperture, shaped optics, a surface RMS of 160 microns, 4-degree slew and settle time in 10 seconds, reference pointing of 3 arcs second RMS, and then, like I said, offset Gregorian design or optics. So then you'll see this, they're designed with their little Mercedes down there. The front end concept is 6 bands and 2 dewars. The 2 lowest bands are wide bands, 3.25 to 1 bands, quad ridge horns. So the L band is 1.2 to 3.5 gigahertz, and then our sort of C-ish the CS band is 3.5 to 12.3 gigahertz. The middle 3 bands go from 12.3 to 50 gigahertz using sort of standard corrugated horns to maximize sensitivity. And then for the band 6, the highest frequency band, we also use corrugated horns with waveguide LNAs with lockdown conversion. For cryo cooling, right now we're doing a 2-stage Gifford-McMahon system, but we're also still looking at a Stirling cooler situation or a solution. There's a trade study out for that, but right now we're sticking with the standard GN cooling. For software and computing, so the operations concept is a science-ready data product telescope. So each observing mode, standard observing mode, the user will submit information via the proposal, which would set up, the observations, and also dictate what the high-level data product that needs to come out of the telescope based on those observations. And that's what the user will get at the end. So this is both for initial observations or archive projects which reprocess existing data. For post-processing, so the analysis shows that storing all the raw visibilities will be tractable when ngVLA goes into operations. Data processing is post facto with a system size for average throughput. The average data rate is just over 7.5 gigabits per second, designed for a peak of 320 gigabytes per second, peak. So a 4-hour observation will generate about 110 terabytes, and it requires about 1,000 cores to process in a few days. So the computing expectation is about a 2 billion core hour problem, which is challenging, but can but the thought is can be met with off-the-shelf solution cluster. This sort of computing is throttled by time resolution, spectral resolution, and multifaceted imaging. So the way we get away with keeping visibilities and not blowing up the compute is we're not going to allow some low frequency full beam AW projection cases. So, we're not going to allow basically the fringe cases, the observing cases that, completely blow the compute budget and the data storage budget. And we'll wait for technology to catch up there. We've been busy over the past year. So for FY21 activities, we hosted a special session at the AAS. We've carried out the community studies that I mentioned. There were 7 approved and 4 funded in the US. The biggest news for sure is being awarded $23 million from the NSF for the antenna development and the prototype. We're really working hard to get through a conceptual design review next year to be MRAFC ready for the NSF. At that point, all the requirements will be baselined. As I said, the award went to MTEX to do this final design and prototype, and we're also ramping up on the preliminary design of all major systems at the same time. High-level goals right now, I'd say the number 1 is to be ready to react to a positive Astro 2020 decadal survey outcome. That is to be released next Thursday that we just found out, which is exciting. Obviously, everybody's probably a little tense, but we're hoping for a positive outcome. We want to continue to advance the ngVLA conceptual design so we can get right into that MREFCQ at NSF. We're going to continue to build and work with the community to hone the science case, finalize the antenna design and prototype, and we're starting to really formalize international partnership. We just had a meeting yesterday morning with potential partners to start to talk about plans post-decadal. And then once the decadal comes out, we're actually going to have to start to look at what the VLA to ngVLA transition plan really starts to look like. And to do that, I think it's going to be led by a community-led working group. We'll carry that out hand in hand with NRAO. Project timeline, this is what it looks like. So we submitted to our project to the Astro 2020 Decadal Survey, which seems like ages ago, and I guess it was back just after 2019. We have the recommendation will come out on Thursday. After that, if things look good, we're going to be ready to submit a proposal to the NSF to become an RFC candidate. With the current antenna schedule, the prototype will be delivered to the VLA site sometime in 2023. Which is very exciting, and then fully vetted and validated probably by 2025. We hope to come out of the NSF, the MRAFC with the final design review right around 2025, and then kick off construction. Early science operations should start sometime in 2029, and then full operations, thank you, in 2035. So perfect timing. So to summarize, community engagement continues, and I think it's only going to increase. If things go well, we're going to be looking to get the community even more involved. Oops, sorry. By various activities, basically observation planning and thinking about key projects. Project management systems engineering is ongoing, and that's ramping up too. We're really working on our conceptual design packet. Industrial and international partnerships are ongoing and building, and very excited to say that we will have an antenna on the plains of San Augustine in 2023. And this has really all been made possible by significant financial support by the National Science Foundation. So happy to take questions now. Thank you. It's nice to hear real clapping.
Thanks very much for a fantastic talk, Eric. This looks awesome, and I'm glad to see you're hiring so many South Africans. Shows you're really serious about this.
Clearly, there are a couple more in our heads too.
We have some questions on Discord. I think the first question is from Peter Tubin. Did the simulations incorporate short spacings? And what's the current thought, how and when the short spacings are observed?
Which simulations? For the planet formation? You don't know. So we actually, we have an ngVLA memo series where we've gone through and carried out the exercise of what the image fidelity is with and without the short baseline array and total power. So we do have those simulations. Whether or not that they're taken simultaneously, I think the current thought is that they don't need to be. The short spacing array will be working on its own, separate from the main 18-meter telescopes.
All right, thank you.
Unless someone requests it specially, right? Unless there's a scientific reason to do it, simultaneously.
Okay, we have a question from the audience. Landman, you want to take a microphone?
Hi, Eric. Thanks
Hi.
for a great talk.
Very well.
I was wondering, how worried are you about RFI and space junk ruining your key science goals?
Yeah, so that's a very good question and something that we are, been actively working on, concerned about. So we have a new RFI sort of task force in-house that is looking at the impact of SpaceX, where SpaceX has actually thrown some money, our way to help to diagnose the impact of their Starlink. And we actually even have some of the uplink things at the VLA site, and we've been testing that over the last month. I mean, so far so good. They don't seem to be blasting away too hard. I think it's what you think it is. If you point at them, you're going to see them. If you don't point at them, it seems a little bit harder. But for the most point, right, interferometry helps us with this, and the longer baselines helps us with this to sort of avoid that interference. So I think we're not, while a concern, and we don't want to give up any sort of frequency space that we don't have to, I think we're feeling like this is a manageable problem.
Thank you.
We have a question from Francois Bonnerel in the chat. What kind of plans for that data archival and open distribution?
Well, that's a good question about the open distribution. We will be running an archive. Exactly what that archive looks like is TBD. But the current thought is that, as I said, raw visibilities will be stored. One can reprocess them. They'd have to propose for it. It's unclear, what the compute cost is there and how frequently we can do it. The high-level data products will be stored so people can access. In terms of, there will be a proprietary period, I'm sure, of a year standard that what we're doing now with current NRAO facilities. But that is a good question. There's even talk of whether or not, partners might come in and want to host their own archives, or we do something distributed. But I don't see there not being some sort of a centralized archive that is run by us.
All right. Final question, perhaps, from David Buckley in chat. What do you consider the most compelling joint science programs that ngVLA and SKA might work on together, which maybe neither could optimally do on their own?
God, that's such a good question. That's a good question. It's hard for me not to go back to my bread and butter, but with a lot of the large area mappings for the extragalactic sky and these tiered surveys that the SK will do, and spend a lot of time on them. For the galaxy evolution studies, going in and taking that statistical information and tying it with the detailed studies of individual systems, both the gas and star formation properties, I think that's going to be a powerful tool for constraining the formation and evolution of galaxies at very high redshift. The SK will see a lot of, because of their large area maps and depth, they're prone to find a lot of new and exciting exotic systems that the ngVLA will be very keen to follow up. And if I studied protoplanetary disks or something, I'm sure I would say something different.
Great, thanks very much. We're out of time, but further questions can be taken on Discord, Eric.
You got it.
Let's thank you, Eric, again.